So we'll see like what are the basics which will be required to understand like these convolutional neural networks, and all these basics we have already covered. So I'll just give you a quick recap of this. Okay, so the general CNN architecture we have already seen. We have this input as image. We have convolution layers, subsampling layers, again followed by convolution, and again we can have several of these layers. This is just one combination. And at the end, we have like fully connected layer, which will give you the predictions. Of course, you can have more than one fully connected layer. Okay, so that's the input. Now let's talk about the input. So input can be, again, it could be one-dimensional signal, 2D, 3D signal. So let's talk about images. Images, we know it's like you can store that as a two-dimensional matrix, and it will have like certain height, certain width. And for each pixel location, or you can say like this grid location, you will have some value. For grayscale, it will be just one value. If it's RGB, you will have three value. Okay, so usually we work on RGB images. In that case, you will have a volume which represents the image, and that volume will be like three-dimensional volume representing height, width, and the depth. So depth in color, in case of color images, will be 3. In case of grayscale images, the depth will be 1. Okay, so that will be your input to your CNN. The second part is the network itself. And this part is like the convolutional part of this architecture, which tries to learn, or you can say extract features from this input sample. Okay, so that's the whole role of this part of the architecture. And once you have these features, you can use those features to perform the classification task. All right, so let's try to understand how this part of segment is actually extracting features. For that, let's go back to filtering. Filtering, we have seen, given a filter and your image patch, you perform this linear combination, right? So if this is your image, this is your filter, it gives you some kind of response. And the idea was it's trying to do some kind of pattern matching. So whatever pattern you have in your kernel, if that pattern is present in your input image, you will get high activation. Otherwise, you will get a very low activation. Okay, so if this is your image patch, again, it's a very small patch of a big image, and this is your kernel. All you do is you perform filtering, which is just element-wise multiplication of these values, and you can just take the mean, and you can just add up those values. Okay, so this is the basic filtering operation, which is performed inside your convolutional neural networks. Okay. So this filtering, I mean, you can have two variations. Either you can find correlation, or you can perform a convolution. We'll briefly talk about that. What's the difference? And the basic difference, like conceptually, we know that they are basically the same set of operations. The only difference is you have to like flip your kernels in both the axes to match convolution with correlation. Okay, so this is the basic correlation operation. It's just taking element-wise multiplication and adding up the values. And convolution is if you flip your kernel, then you can again perform the correlation operation. Okay, so you have two extra steps. And we talked about edge detection, where what we did is we have this Sobel kernel, which was, and you are also doing this for a programming assignment. And it's trying to, if you look at this filter, it's actually trying to find edges. That's what this filter represents, because the values are changing in the X direction. And in this one, the values are changing in the Y direction. Okay, so that was the algorithm for Sobel. But the idea is, again, you are just doing filtering here. And what you're doing is whatever filter you have, you're trying to find that pattern in your input image. If this pattern is present, your outer activations are going to be high. So that's the whole idea about this center segment of your convolutional architecture. You will have these kernels here. We'll talk about that later. So those kernels will try to find the patterns in the input image. Okay, and it's not just one step. You will keep finding that patterns as hierarchy. So you'll find patterns in the input image, and then you'll try to find patterns in those patterns, and you keep doing that. So that's kind of a composition. And at the end, that's going to give you features, which you are going to make. I mean, classification, you can use those features for anything. For classification, for detection, or semantic segmentation. Okay, so this final layer, as I said earlier, it's like a simple fully connected layer. which is a multi-layer perceptron, and we just discussed this in the previous lecture. So the extracted features from the image are treated as input to this MLP, and then we make predictions about like what, let's say, image classification, what object is present in these set of features. Okay, these are also called feed-forward neural networks. Now, so that was like a brief overview, and we have also seen this learning process, the whole pipeline, how we train these models. So again, we don't train on like single images. We have like the full training set, right? Given a huge data set, we split that into training and testing and validation. So these features in case of CNN are extracted by that CNN part. All right. So this CNN part will give you these set of features. So this, I think we just covered in the previous lecture, like what's the difference between neural network and convolutional neural network. And one big difference was neural network actually worked on flattened set of features. We don't preserve the spatial structure. In CNN, we are preserving the spatial structure. So that's one positive. The other is like, while we are doing that, we are able to actually share the weights. So which reduces the memory consumption of the network. And later we will, when we do the case study, we'll see that like how that reduces the amount of weights we need in a network drastically.